Hello, class. I am going to do the first lecture of today. So I took the morning off a little bit. Let me start the timer. I've been thinking about this lecture after the Dimensions and Units lecture. And of course, in the Dimensions and Unit lecture, as you've been reading through your textbook, Alexander and Sadiku, you probably noticed that I've already covered a lot of things to do with charge transfer, that basically an amp flowing through a wire. I'm just going to say it again. If I have a wire, in fact, I'll make this wire a three-dimensional wire now, right? If I have a wire and I have current that's flowing through that wire, 1 amp of current for 1 second, that equals 1 coulomb of charge that has gone through there, right? So the amperage, the current, times the time the current is flowing through there equals the amount of charge, right? So current times time equals charge. All right? Because really what current is the change in charge over the change in time. So that's all I'm really saying there. Anyway, you've got some homework problems to do on that, and I'm sure you will. So anyway, I noticed that I've really talked about a lot of those things and a lot of the things that are covered in there. And so really I'm going on to chapter 2. Maybe the final part of chapter 1, but chapter 2 as well. And there's 2 equations that we really, from the very beginning, as I said in the earlier lectures, have to master, and that's P equals IV, the power equation. I'm just going to box that in because it's so important. And V equals IR, Ohm's law. So straight off the bat in this, I think this is the 4th lecture, we want to handle those 2 things and look at those 2 things and how they interplay with one another. And earlier in our lectures, I actually put these 2 together to come up with what in high school they usually term the 3 power equations, but of course they aren't 3 power equations, it's just 1 power equation. And so what I'm going to do is I'm going to say that the power then is equal to, and let's replace the V in there. So I've got I squared R. I'm not going to write it out twice this time. So P equals I squared R. And then P, if I was to switch that around and solve for I equals V over R and substitute that into the power equation, that's of course going to say that P equals V squared over R, right? So really, when you look at it, those are the power equations. This is the power equation, but these are the other 2 ways that they're expressed, and that you can look at it and manifest itself. Of course, that's just using Ohm's law of the voltage drop across a resistor is equal to the current flowing through the resistor times the resistance of the resistor. And that's the first thing that I want to look at right here. Let's say that I just had this circuit. Now when we talk about drawing AC and DC circuit convention, this is usually, you'll see this in 2 forms, either 4 bars or 6 bars. I'll write the 6 bar one, right? Something like that. That would be your DC voltage source. If I was doing something that was an AC source is a circle, and it has a plus and a minus. Of course, with an AC source, you don't really have a plus and a, you solve the circuit with the plus, always looking at the current then flowing out of this going in this positive direction. That's how you solve the circuit. But of course, what's really going on with an AC wave is you're seeing something like this, where on an AC waveform, you've got positive voltage, negative voltage, positive voltage, so on and so forth, right? So you've got positive voltage and you have negative voltage. It's seesawing back and forth. So it really, you know, this specifies here that this is connected to a circuit and this is a reference voltage. It stays the same all the time, right? DC voltage, when we look at DC voltage, if we looked at it on the same thing as we have here, this is time and this would be amplitude. If we did that same thing, of course, DC voltage would be a straight line, wouldn't it? DC voltage is always the same voltage, like a battery, 1.5 volt battery, always 1.5 volts. That's a DC power source. But the 120 volts that's coming out of your wall, that's an AC power source. And we'll talk about that maybe, you know, later on as we get toward the end of the semester and I introduce you into some AC understandings, you know, understanding of AC, getting you ready for the Network Theory 2 course that you're going to have. We'll see how fast I can get through all of this other stuff, though. Now, let's look at a resistor, right? So we know how to write power sources here, but let's look at a little, just a little circuit. I'm just going to use the 4-line notation now for a DC power source. And let's just put one resistor. That's what a resistor looks like. In fact, if we wanted to look at how all of the various different components that we're going to see throughout the semester look, that's a resistor. That is a capacitor. And this is an inductor. Inductors are also called chokes or coils. Chokes are coils. Coils because they look like a coil, an inductor because that's their name, and a choke is because they can, you know, sort of choke back current in a circuit. So anyway, this is a resistor. And let's say that this resistor is 500 ohms. All right. Now the rest of the circuit, as you can see, when we draw a schematic of a circuit, we sort of draw it in a box manner, don't we? Right? And you guys might be familiar with that. Now let's give this a value over here. What value would you like me to give that? 10 volts, DC? Sure, absolutely, no problem. So now I've got 10 volts DC here, and that's flowing through. That's all connected. There's no switch there, nothing that's open in that circuit. That circuit is a totally closed circuit. So now I've got 10 volts, and it's going across a 500 ohm resistor. Let's look at Ohm's law. V equals IR, right? So we've got 10 volts equals I times 500 ohms. Well, that's one equation and one unknown. It's just a little algebra, isn't it? So that says that I, the current that's flowing out of the power supply. Now, how do I know it's out of there? Because this part here, look on the power supply, the longest line on my DC power supply is the positive. And the short line down here is the negative. And the way that you can remember that is, you know, sort of like a battery. This is the short line. It's a negative. Hey, which of the two lines, the long line or the short line, looks like a negative? That's right. All you have to remember is that the short line is a negative, and of course the short line is a negative here. And we know that current, now not like electrons, because electrons flow in the opposite direction of current, right? But current flows from positive to negative. So we get the current that's flowing out here. There's no other place in there that it can go. It's just going around in a circle, right? So my current is just flowing around in a circle. So all of the current that comes out of the power supply at the positive end here, I'll write positive, although I don't really have to. Out of the positive end here has got to go through that resistor, and then it's got to go all the way around and through the short circuit from this end of the resistor all the way around here, because that's just a piece of wire, right? So that piece of wire right there is a short circuit. I might as well have connected this right to the other end of the battery. And I did. I'm just drawing it this way because it makes it easier for you to see, right? So what is my current then? Well, I'm just solving that. That would be 10 volts, right, divided by 500 ohms. 10 volts divided by 500 ohms. Well, I better get my calculator out. Not, but whatever. 10 volts divided by 500 ohms gives me 0.020 amps, right? Now what is that? Because we could put 0.020 amps, but why not talking milliamps? So that would really be equal to 20 milliamps, wouldn't it? And that's what we use as engineers. We always use the integer of 3 power of 10s to do that. And we want to keep doing that, right? So we've got 20 milliamps of current that's flowing through there. Right. Does that work out if I take that 20 milliamps and I multiply it by the resistance? Will I get 10 volts? Yes. So I know that this over here on this side is 0 volts, and I know that that's 10 volts, right? That power supply that's going around there. We're going to throw another resistor in there in just a second. Don't get ahead of me, right? Well, because what I want you to do is remember that this lecture is, did I even turn that on? Yes, I did. Boy, that was thinking. I usually can't remember those things. So that's right. Don't get ahead of me. But here's what I want to do. It's a power and Ohm's law lecture, right? So what is the power through that resistor? Let's look at that. So the power through that resistor is the voltage drop across the resistor, right? Voltage drop across the resistor times the current through the resistor. Well, the voltage drop across the resistor, let's see, over here on this side, it's 10 volts. Down here, it's 0 volts. So I guess that's going to be a 10 volt drop. So my power, right, that's being dissipated in the resistor is 10 volts times the current through the resistor. And I'm just going to write this in the original format that we had, 0.020 amps. I don't want to write it in the 20 milliamps, do I? No, because if I wrote it in the 20 milliamps, then I would have 10 milliwatts. I don't want that. I want it in watts. I'll change it to milliwatts. If I want to change it to milliwatts, I'll just see how it comes out. So let's do that. So 0.020 amps. Now I'm multiplying two primary units, right? I shouldn't say primary, but units, derived units from primary units. Voltage times amps. There's no millivolts, there's no mega amps, there's nothing. So when I multiply this out now, I don't know why, no, there you go. So when I multiply this out now, I'm going to get 0.2, but 0.2 what? Volts times amps. Volts times amps. Everybody knows it's already power. So I should, of course, volts times amps, things cancel out, and I end up getting watts. Because it's power, right? So there you go. 0.2 watts is being dissipated. How is it being dissipated in that resistor? It's being dissipated by heat, right? 0.2 watts. Now, why did I do this analysis for something like this? Because I wanted to know, can I use 1/4 watt resistor, right? So you're doing a power analysis to see if a 0.25 watt resistor would work in that situation. Now you actually figure this out, and you figure out, well, it's 0.2 watts. Yeah, I guess I could use a 0.25 watt resistor in that application, couldn't I? But do you really want to? Isn't the engineering safety factor 2 usually? So if I'm using an engineering safety factor of 2 in an application that I'm designing for, and I see that, this circuit right here, that resistor right there is going to be dissipating 0.2 watts. Can I use a 1/4 watt resistor, and that's 0.25 watts? I would say no. I would say no. I have to go to a higher wattage resistor because I need at least a 0.4 watt resistor. You'd have to go then to a half watt resistor because you really need a 0.4 watt resistor, and the closest thing to that would be a 0.5 watt resistor, a half watt resistor that you could use rather than the 1/4 watt. Would the 1/4 watt get you by? Yeah, probably would, but that's not folding in the engineering safety factor into your design. And that's something that you should always be aware of and consider, because liability insurance for companies, especially manufacturing companies and design companies, is very high for that exact reason, because they're sued. Okay, now we've done this and we figured that all out. I just want to draw a line across there. We figured that all out for a 1 resistor system. Now let's just go one step further. Let's say that I now have, I'm still going to use my same 10 volts, but now instead of having 1 resistor, I'm going to have 2 resistors, right? Now these resistors are going to be in series. Now this resistor right here, I'm going to say is a my old 500 ohm resistor. And then this resistor over here, I'm going to say is a 1000 ohm resistor. Still, this will be grounded, just like it was up here. I should have put a ground on that. And so that we know that this is going to be 0 volts, and we know this is going to be 10 volts up here, right? Because the long line is always the positive. Now, as we look at this, we're still going to have current that is going to be flowing out. Why don't I use my multicolored pens? I got to see if this pen works, actually. That would be great if it did. And then I could have, oh, look at that. That's fantastic. I didn't even think it worked. So we're still going to have our current that's flowing all the way around the circuit. The same current that is flowing through the first resistor is the same current that's flowing through the second resistor. And the way that resistors add together when they're in series is just one resistor right after the other. So in series, the equivalent resistance, right, for series circuit, I'm going to just write that here, series, because parallel is not like this. But the equivalent resistor for a series circuit would be R1 plus R2 plus however many more R's you've got, right? And you add them all together. And so we've got 2 here. We now know that the total resistance for that circuit is going to be 500 plus 1000, because you just add them together. So my total resistance for that circuit is going to be 1,500 ohms. Does everyone see that? I think everybody, really doesn't have a problem with that, and we've mastered Ohm's law and stuff like that. So let's keep going. So 1,500 ohms is the total resistance for the circuit. But we know Ohm's law, don't we? V equals IR. V equals IR. And we can solve that for I. I equals V over R, or 10 volts divided by 1,500 ohms. Right? Now, isn't that going to be just 1/3 of what I had up here? And I had 0.02 there, so 1/3 of that is going to be around 0.066666. Isn't that what everybody's thinking? Let me just punch that in here because I like to, think up numbers as we're working it. Yep, that's what we've got. 0.006667 amps. Now, that would be 6.667 milliamps, wouldn't it? But we don't want to use milliamps when we're actually doing the calculations. We always want to revert everything back to the most compact defined units as we can. I mean, you don't want to use millivolts and then say to ourselves, okay, I'm using millivolts, but I know that I've got to divide it by divided by 1,000 when I get the answer. Don't ever say that. Don't ever say it. Always put things back into volts, amps, when you put them into your calculator. It's just you're just asking for trouble otherwise. All right, so anyway, we've got the 6.667 milliamps. Now we've got two resistors, and in fact, I'm going to make a point there in the circuit, halfway between those two resistors, and sort of see what the voltage is there. We know the voltage right here coming out of the source is going to be 10 volts. We know the voltage right here, because this is all grounded, is going to be 0 volts on the other side of that. So let's look at what the voltage would be at A. Now we know that the current is going around in a clockwise fashion, right? And so if it's going on a clockwise fashion, if this is the input of the current and this is the output of the current through that resistor, then if the current is flowing in that direction, there's going to be a voltage drop. Voltage drop. I'm going to put negative voltage drop. Okay, negative. So this is going to be higher. This is going to be lower. But how much higher and how much lower? Well, this is definitely going to be my 10 volts, right? So we're going to be subtracting whatever that voltage drop is off there. So my voltage at A is going to be the 10 volts that I started out with minus the voltage drop. And what is the voltage drop there? Isn't it just the current that's flowing through it times the resistance of the resistor? So that's what we're going to put in there, the current that's flowing through it, and we know that it's 0.00667 amps, right? The current that's flowing through it times the resistance of the resistor that the current's flowing through, which should be a 500 ohm resistor. All right, well, we can easily calculate that. 500, it's going to be, I suppose, 3.333. And exactly right. So 10 minus 3.33 volts gives me 6.667 volts. So the voltage right here at point A, voltage at A, equals 6.667 volts, which is what we would expect it to be, right? Because we've really got 3 units of 500. 500, I mean, what if instead of putting 500 and 1,000 here, I put 1 and 2? I mean, I could have done that because we're looking at it, we would have gotten some other different things. This is a little more realistic, of course. But let's just look at that. So that's my voltage drop across each one of those, right? Now, let's say that I have 10 volts at this end, right? I've got 10 volts here, and I'm going to go through a series of resistors. Let's see. So at this end, I'm going to have 0 volts. At this end, I'm going to have 10 volts. What's my voltage all along here? Now, what I'm going to do is I'm going to make each one of these 1,000 volts or 1,000 ohms, right? So R equals 1,000 ohms, and this is R. I won't keep saying R over and over again till I'm done, because you can see that they're all R. Now, what we want to do is we want to find out what is the voltage at each one of these locations. Now, they're all exactly, I think you're already probably seeing what's going on here. They're all exactly the same value, aren't they? And they're all 1,000 ohms. I made it 1,000 ohms because you can easily see that I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's going to be 10,000. So my actual current that's going to be going through there is 10 volts divided by 10,000 ohms. I'll extend that out a little bit. 10,000 ohms, and that's going to give us 1 milliamp, which would be 0.001 amp. As our current, right? I use small i's, I use big i's, so does your book. And so that's the current that's going to be going through here. Well, let's see. Now, if that's 1/1000th times 1,000, doesn't that cancel each other out? Right. So the voltage drop across here is 1,000 times 1/1000th, and that would be 1. So my voltage drop across here is just 1 volt. So at A, my voltage at A, right, is going to be 9 volts. My voltage at B is going to be 8 volts, so on and so forth. Now, I just wanted to sort of talk about that for a second. I still want to go back up here and finish this problem up, because remember what the topic of our lecture was: power and Ohm's law. So let's go back up here and look at the power that's being dissipated by each of those two. Now, here's what everybody's going to probably say as well. If that's 500 ohms, that's half the resistance of 1,000 ohms. So the power that's being dissipated by the 500 ohms is probably 1/2 the power that's being dissipated by the 1,000 ohms, since they both have the same current that's flowing through each one of them, right? And that's absolutely correct. In fact, if we looked at the power, let's look at the 500 ohms first. So power of the 500 ohm is going to be the voltage drop across that 500 ohm, and we know that that's going to be 3.33 volts times the current that's flowing through it, which is 0.00667 amps. And I'll tell you what that gives me in just a second, because I've got the thing right here. 3 times, that gives me 0.0, well, yeah, 3, yeah, 0.020 watts, right? So for the 500 ohm here, I'm actually dissipating 0.020 watts. Instead of this over here, now the 1,000, I would be dissipating the other 0.404 watts, because this would be 6.66 instead of 3.33. Same current, but this would be 6.66. So P for the 1,000 watt is just going to be twice that, or 0.04 watts, right? So it's a total of 0.6 watts. Yeah, whereas over here, you know, you've got 10 volts across that, and so you have a, or you only have 500 volts, so you've got a higher current that's actually flowing through there, whereas you've actually got 3 times the amount of current flowing through up here, because you have 1/3 the total resistance. Just thought that I'd point that out. And I think everything else is fine. We could figure out what the power is going through here, but I think everybody can already see that. If I have a 10 volt, I mean, using all of these resistors, if I have 10 volt drop from here to here, and they're all exactly the same, the 10 volt drop and the current that's going to be flowing through there, which is a 1 milliamp current, that's going to give me a 10 milliwatt circuit that I have there. That's with all of the resistors that I have. All right, does everybody see how that goes? P equals VI. All right, that's the end of our power and Ohm's law lecture. Now we're going to go, the next lecture is really going to look at Kirchhoff's voltage and Kirchhoff's current laws. Okay, I'll see you there.